Okay. So in today's class, we will be continuing the theories about the Maxwell's law and how we can use the Maxwell's law to derive the wave equation. Right. So continuing from the last class, I will write something regarding that. So we discussed about the propagation of electromagnetic waves in the last class, right? Propagation of electromagnetic waves in the last class. So in that class, we were discussing about varying current across a simple conductor. And we discussed about how an loop of magnetic field is created. So we denote it like this. So the magnetic field is created around the conductor, and the magnetic field that is created is also varying with the time. So because of the varying current which is used to produce it. So if we have the varying current, the magnitude of the magnetic field that is generated is also varying with time. So then we have the generation of electric field due to the varying magnetic field. So we have the generation of the electric field due to the magnetic field. And then due to this electric field that is generated, we have the generation of magnetic field, right? So these phenomena are happening because of the laws that define the concept that a varying current can produce a magnetic field, right? So that was present to us by Ampere's law, right? So using Ampere's law, we learned that by varying some electric flux, we can produce a magnetic field, and the magnetic field will be generated as a curl around the varying electric field. So in here, initially, the magnetic field is created as a loop because of the varying electric field and its effect that has been added to the environment. And because of that, the loop of magnetic field is created. And once you have a varying magnetic flux, you can create a varying electric field. So that principle was proposed by Faraday's law. So, however, although these laws were like proposed by Ampere's law and Faraday's law, Maxwell told that the rest of the wave will be continuously getting generated because of the presence of the previously generated electric field and then the magnetic fields. So the fact that the electromagnetic wave can propagate without like a specific source in the free space was proposed by Maxwell. So Maxwell presented the idea that you don't need a specific energy source all the time to generate an electromagnetic wave. So electromagnetic wave can propagate in free space without independently after it has been initially generated using some source has been initially generated, which has been initially generated using uh, a varying current, a varying electric field, varying current, or a varying magnetic field, right? A varying magnetic field, right? Or varying electric field, we can say, right? So after this electromagnetic wave has been initially started or generated at one point in the space, the electromagnetic wave can propagate on its own using the loops, the electric field and the magnetic fields that has been generated uh, in the previous time instances due to the source. Right, I hope it is clear. So the Maxwell, the speciality or the unique contribution of Maxwell was proposing that the uh, electromagnetic waves do not need a specific source in the specific source in the free space to support its propagation, or to support its propagation right? After it has been initially generated using a specific source, right? So it has been generated using a specific source, right? So once it had been already generated at one point, the rest of the generation of the electromagnetic waves can be managed by the varying electric fields and the varying magnetic fields that has been created as a result of the uh, initial source of varying current or varying magnetic field, right? So that is basically the Maxwell's contribution to the idea of electromagnetic waves getting propagated in the free space, right? So about the free space, right? So free space is a space where there's no free electric charges or any kind of like particles or matter, right? So free space is somewhere we don't have any particles or electric charges or matter. So even in this kind of a free space, the electromagnetic wave can propagate without any support from electric charges, particles, or matter, right? So you know that, right? So you know the fact that we initially need electric charges and moving electric charges to generate the magnetic field. Initially, we need that. However, after we have generated the electromagnetic wave, we do not need the support of the electric charges, moving electric charges, or varying magnetic field to actually we need the varying magnetic field to uh, uh, like create the consequent electromagnetic waves. But initial as the source, we don't need a source all the time in between to keep generating the electromagnetic wave. And especially in free space, it will continue to propagate without any attenuation, because in the free space, we do not have any medium which will disrupt or attenuate the wave. All right, so if you have any questions, you can ask, right? So that is basically regarding the electromagnetic wave propagation, right? So in this class, we have to learn about the wave equation derivation from the Maxwell's laws. Right, so I'm going to delete these, right? So we need to show that Maxwell has said that Maxwell has proved mathematically that wave can propagate without a certain electric source, electric charge, or moving current in the free space, right? We have, right? So Maxwell's idea that an electromagnetic wave can be generated without a certain varying current can be shown using the wave equation, right? So we need to show this using Maxwell's law, right? So Maxwell's law. We are going to derive the wave equation using Maxwell's law, right? So wave equation using Maxwell's law. Right? We are going to derive the wave equation using Maxwell's law, right? So in order to derive the Maxwell's law, first wave equation, first we need to make some assumptions, right? The first assumption is that the wave will propagate in the homogeneous medium. Homogeneous medium with a permittivity epsilon, right? Permittivity epsilon and permeability mu, right? Permeability mu. Okay, so we are assuming that a wave will be propagating, right? A certain the certain wave will be or propagating in a homogeneous medium with a certain permittivity epsilon and permeability mu, right? That is the assumption that we are making. So actually we are going to prove that this electromagnetic wave is a wave. However, like we are going to assume that whatever that is propagating in a homogeneous medium with permittivity epsilon and permeability mu. Okay, so in here I would like to explain what permittivity means. So ability of a material to store energy within the medium, to store electrical energy within the medium. Okay, so basically the permittivity means that how much of ability does the medium has in order to generate electric fields, which means that how much of ability the medium has to store electrical energy, right? Those are both same. So permittivity gives us the idea like how much of electric energy can be stored in a certain medium. And permeability means how much of a ability that a material has to store to generate magnetic fields. Right? So basically, we are going to assume that whatever that is getting generated in the space will propagate in a homogeneous medium with the permittivity epsilon and permeability mu. The medium has permittivity epsilon. That means the medium has the ability to store electrical energy within the medium of this epsilon naught amount and the medium has the ability to generate magnetic field in the value of mu. Okay, so mu gives the indication about how much of an ability the material has to generate magnetic fields. Epsilon gives us an idea how much of an ability the medium has to store electrical energy, or in other words, how much of ability that medium has to generate electric field. Right, so you can easily remember the meaning of the permittivity and permeability. Apart from that, the homogeneous medium. So what do you mean by homogeneous? A homogeneous means it has uniform composition all throughout the medium. It has uniform composition all throughout the medium. Okay, so we are going to consider a scenario where there's a wave propagating in this homogeneous medium with permittivity epsilon and permeability mu, right? So for this scenario, we are going to derive the wave equation, and we are going to show that an electromagnetic wave that is getting propagated in a free space is actually following the properties of a wave, right? So we are going to derive that now. Right, so wave equation derivation we are going to do. So we are going to derive the wave equation using the Maxwell's law, right? By doing that, we are actually showing that the Maxwell has presented laws which show us that electromagnetic waves are actually propagating as waves in, for example, that we can observe in classical physics. And then electromagnetic waves show the same behaviors as wave behavior. So because of that, we can represent our electromagnetic waves as a normal wave with certain frequency, wavelength, amplitude, and so on. So therefore, we are able to easily analyze and do mathematical computations on these electromagnetic waves, right? Apart from that, we can consider different complex scenarios, and based on the wave behavior, we can like estimate the wave behavior at a certain medium, right? At a certain medium. Anyway, so we are going to derive the wave equation for the electromagnetic waves using Maxwell's law, right? I'm going to delete this page, right? So if you have any questions, you can ask, right? So wave equation derivation, wave equation derivation for a free space, right? Okay, so for a perfect homogeneous vacuum or homogeneous free space, right? For a perfect homogeneous medium with permittivity epsilon naught and permeability mu naught, we are going to derive the we are going to consider the Maxwell's law, and we are going to derive one equation which is called as the wave equation, right? So we are going to consider a homogeneous medium where the composition of the medium is equal in every part of the medium, and we are going to consider that the permittivity is epsilon naught and permeability is mu naught, right? So actually the value of epsilon naught defines the permittivity of the free space, and the permeability mu naught means the permeability in the free space. So in general, epsilon naught and mu naught are values that we define for the free space, right? Permittivity value and permeability value that we define for the free space are given as epsilon naught and mu naught. From Faraday's law, we'll start with the Faraday's law, right? So Faraday's law, we can define using this equation, right? So this is actually the differential form of the Faraday's law, right? So this is the differential form of the Faraday's law, right? So actually differential form is much more simpler than the integral form, right? We are going to start with the differential form of the Faraday's law. And then we are going to take the curl on both sides, curl in both sides. We are going to take the curl in both sides, right? So once we take the curl in both sides, we are left with something like this. Okay, so once we take the curl on both sides, we can take the curl function into the differentiation and we can write like this. So we are left with something like this, right? So then we can write as curl of curl, right? Curl of curl can be written as, right? Can be written as, right? Delta dot E minus Laplacian E, right? And then we can write as minus dabba curl of B over dabba T. And then we can name that equation as A, for example, right? And then so this equation I got by taking the mathematical equivalent of this expression. Okay, so using mathematics we can write this expression as the solution of this curl curl of E, right? So that expression we can express in a different way mathematically using this expression. Okay, so this is a mathematical conversion, okay, of this first expression, right? Of this expression, we can denote this first expression using this notation. Okay, so that is done mathematically. After that, we can also simplify this further using this assumption where we take the divergence of electric field is 0, right? So why do we take this assumption into consideration, right? So we are assuming, or we are actually deriving this electromagnetic wave, wave propagation scenario for a scenario where we do not have any free electric charges, right? So therefore, we are considering a medium with we are considering the we are considering the we are considering this wave propagation or this propagation under a certain medium where there's no electric charges, right? So I will write it with, right? We are considering a medium where there's no free electric charges, right? We are considering a medium where there's no free electric charges. So once we do not have any free electric charges, the divergence of the electric field in that medium is going to be 0, right? So we can take this as one of the one of the equations to simplify the equation number A, right? Apart from that, we also take another equation into our help, right? Which is the curl of B is equal to mu naught epsilon naught dabba E over dabba T. This is also we are going to take as help, right? So this is actually the first Maxwell's law. This is first Maxwell's law, right? This is first Maxwell's law. This is the second this is the fourth Maxwell's law. Fourth Maxwell's law, right? So in here, you will see that in the fourth Maxwell's law, usually there was a expression or a term where we had a mu naught J, right? The mu naught J part is 0 now, right? The mu naught J is 0 now. The reason is there's no free electric charges, no free electric charges in the medium, and therefore we are not having any charge density or charge current produced. Right? So there are no free charges, in the medium we are considering, and therefore the mu naught J value is going to be 0. no free charges, mu naught J is going to be 0. Right? So because of that, the fourth Maxwell's law can be written like this. Using these two conditions, we can simplify the equation A further. Right? So we can install we can substitute this expression into here, and we can substitute this delta dot E, right, into here, right? By doing that, we can simplify this equation further, right? I will write the simplified equation now at the top, right? I will write it at the top. But I will write it at the top in here, where this is minus Laplacian E equals mu naught epsilon naught, and E, like second derivation of electric field with respect to the time, right? So this is the final expression you get after substituting substituting the curl of B inside this bracket in the equation A, right? I hope it is clear to you, because mu naught epsilon naught are constants. You can get it out. You are left with two derivations of dabba over dabba t with respect to time of E. Because of that, you are left with the second derivative of the electric field with respect to time. Right? I hope it is clear to you. If it is not clear, you can let me know. Right? So if you cannot, I don't know whether you can understand. So what I have done is, the equation A, if I take from equation A, I have taken the simplification as 0, because the first term in equation A is going to be 0, because I have taken that delta dot E, or the divergence of E, is 0. So because of that, the first term is going to be 0. I have taken it as 0. So in the equation A, the first term is 0 minus Laplacian of E. Right? Laplacian of E is remaining. Right? We cannot solve it any further. It's remaining. And then what we do is, we take the second derivative of the electric field, or this expression with respect to time, over 2 times. So because of that, we are left with this equation, which gives us that the electric field, the Laplacian of the electric field, now this is the Laplacian of the electric field, is equal to the minus of the mu naught epsilon naught into the second derivative of electric field with respect to time. Right? So that is the equation that we are left off after doing the simplifications. Okay. If you have any questions, please ask, right? Right. After that, now we are going to make similarities, right? So now we are going to make this equation similar to the equation, right? So actually, we can solve this, simplify this further. We can write, removing the minus sign on both sides, we can write that this equation is equal to this, if Laplacian of E is equal to mu naught epsilon naught, and like second derivative of the electric field with respect to time. So actually, this is known as the wave equation, right? However, now I need to prove you that this is the wave equation, right? So in classical physics, right? In classical physics, we we have a similar equation which shows us, right? So I will not say that this is the wave equation right now. I will say that in classical physics, we have the same equation, same form of equation, where it says that the Laplacian of the displacement is equal to 1 over the velocity squared into the second derivation of the displacement with respect to time. Okay, so this is the equation that we have in classical physics regarding the displacement of a wave with respect to the time, right? So if we have a certain wave, right, we have a certain wave in classical physics where we learn about the waves, it says that the displacement that we have at a certain time, right? The displacement that we have at a certain time, we can denote using simple y. That displacement that we have, once we take the behavior of that displacement, it will follow this equation, right? This has been proven by physicists, right? So physicists have proven that the displacement of a wave is following this equation, right? And then now this is the format of an equation that follows a certain wave-like behavior, right? So that behavior can also be seen in this equation also, right? I hope you can see that the same type of equation is seen in this B equation as well, right? So we have the Laplacian operation in both the equations. We have displacement, and in here we have electric field. So everywhere where there's displacement, there's electric field in this B equation, right? Everywhere. Apart from that, in here we have a constant. The constant means that this is a velocity, right? So normally, like for a certain medium, the velocity of that wave propagation is a constant. And then in here, this mu naught epsilon naught value is also constant for a certain medium, right? So therefore, this parameter is dependent on the medium and it is constant for a certain medium, right? And also we can see that in here we have the double derivation of the partial derivation with respect to time, and in here also we have the same operation, right? Because of that, we can say that the equation B and the equation C, let's say, are similar, right? B and C are similar, and therefore we can state that uh, the equation B is behaving. B is showing wave-like behavior, right? So equation B is showing wave-like behavior, and therefore we can conclude that E field is showing a wave-like behavior, right? E field is showing a wave-like behavior, right? So E field is showing a wave-like behavior. So right? So therefore, we can say that E, or the electric field, is moving. Electric field is showing a wave-like behavior. It is moving as a wave, right? And magnetic field is also similar, and we can show the same equation for the magnetic field, and we can show the conclusion that magnetic field also is behaving as a wave, right? So this fact we can denote uh, electric field is behaving as a wave. And magnetic field also we can show that is behaving as a wave. So uh, using all that conclusion, we can draw a figure showing the behavior of electric field and magnetic field in a certain medium. Let's say in a free space, right? So the behavior of electric field and magnetic field, let's say first the electric field will behave as a wave, right? Electric field will behave as a wave in a certain medium, right? The depending on the medium, the amplitude of the electric field wave will differ, right? If we take this is as a free space and lossless medium, then we can take the amplitude of the wave is not varying with the time, right? So since there's no medium in the free space, the amplitude will not vary over the time. Let's say the amplitude is same at each position in this medium. Apart from that, we have shown that magnetic field also, I mean, similarly, we can show for the magnetic field also, magnetic field shows a wave-like behavior, right? So magnetic field shows a wave-like behavior, right? So the magnetic field wave-like behavior we can show using this equation. or else we can write it also as the Laplacian of H equals mu naught epsilon naught dabba squared H over dabba T squared, right? So the reason I will explain the uh, B, which is the magnetic flux density, can be related to the magnetic field. So magnetic field is related to B in this manner. So once I substitute mu H in all these places where B occurs, I can take out the mu parameter out of the equation, and I can be, I can be left with the H parameter on both sides. So by this equation, we can say that the magnetic field also follows a wave-like behavior. So because of that, now if we take that electric field using this wave, right? We can show the magnetic field also behaving as a wave. However, magnetic field will propagate in a perpendicular direction to the electric field. That also we can prove using the Maxwell's laws. Anyway, for the moment, I will draw the direction of the magnetic field to be perpendicular to the electric field direction, right? So the electric field is one direction, and then we have the magnetic field, which is perpendicular to that direction and with a equal amplitude in that medium, in this free space, right? Only in the free space we will have, I mean, only in this free space we will have this no attenuation case. Also we will have that situation if we do not have any if we do not have any attenuation factors, and if we do not face different different medium which can prevent our which can reduce our amplitude, and also other factors like attenuation factors such as reflection, scattering, absorption likewise. So wave attenuation can happen due to different reasons, right? In this case, we will take that there's no attenuation in the wave, and therefore there's no attenuation in the amplitude of the magnetic field in this case, right? So we have the magnetic field behaving in the perpendicular direction to the electric field, right? So magnetic field will be generated in the perpendicular direction to the electric field. So the combination of these two effects will generate this wave which will be propagating in this direction, right? So if we have the magnetic field in this direction and the electric field in that specific direction, right, where the electric field is in this direction and the magnetic field is in this direction, then the wave will propagate in this direction, right? Wave will be propagating in this direction, right? So therefore we can say that the wave is propagating in this direction, right? So if we take that this direction to be z axis, then the wave is going in the positive z direction, right? Positive z direction. Wave is going in the positive z direction. Okay, so that is how where the wave is propagating. Okay, I hope it is okay with you, right? Apart from that, now we have shown that the Maxwell's law. Now we have shown that the Maxwell's law proves the fact that an electromagnetic wave can propagate in free space without the existence of propagate in free space, can propagate in free space, uh, independently, independently without the sources that produce them, right? So the electromagnetic waves can propagate without the help of the sources that produced them. Okay, so without the source that produced them, electromagnetic wave can propagate in free space independently. That is what Maxwell's law proposed, right? So how did we show it? By taking the assumption that the free space do not have any uh, electric charges, therefore the divergence of E is 0. Then we also take another assumption where the curl of B is equal to mu naught epsilon naught, and the variation of electric field over time, uh, because the free charges are not available in the free space. Okay, so by taking mainly these two assumptions, right, we were able to show that the wave-like behavior shown by the electric field and the magnetic field, and by doing so, we were able to show that the wave can exist, a certain electromagnetic wave can exist independently without the support of a source that created it. Okay, so that is basically regarding the Maxwell's law. So if it is not clear to you, please let me know. Right, and then now we are going to going to compare this equation, wave equation, with the classical physics equation, and we are going to show the velocity of the wave propagating in the free space, right? So for the free space, we can find the velocity of the electromagnetic wave using this wave equation for B, right? So by comparing, right? So by comparing the equation B with the equation which I call as the classical wave equation, which I can denote using 1 over velocity squared into the displacement over with respect to time, the second derivative of displacement with respect to time, right? So by comparing the equation B and C, I can relate these two parameters that are constants in these two equations, right? I can relate these two parameters as velocities in the wave, right? So mu naught epsilon naught is a velocity, or 1 over velocity of the electromagnetic wave, right? So I hope it is clear to you. I will mention again. So in here, in the classical equation, in the classical wave equation, this parameter gives the 1 over velocity of the wave, right? 1 over velocity of the wave, right? So therefore, we can say by similarity that this parameter in the wave equation should be 1 over electromagnetic waves velocity, right? We can say like that, right? So that we can equate to mu naught epsilon naught, right? So now we are talking about the free space, right? So in order to find the electromagnetic waves velocity, what do we need to do is we need to in here, the electromagnetic waves velocity into squared is equal to mu naught epsilon naught. The reason is in here we have 1 over velocity squared, right? So 1 over em velocity squared is equal to mu naught epsilon naught, right? And then we can say, right, we can say that 1 over mu naught epsilon naught and its square root is equal to the electromagnetic waves velocity, right? Once we substitute the necessary values to mu naught and epsilon naught, right, we have the values that are standard values for mu naught and epsilon naught, by substituting those values in here, we can find out that the velocity of the electromagnetic wave in the free space is equal to 3 into 10 to the 8 meters per second. Okay, so the velocity of the electromagnetic waves in the free space is equal to the speed of light. Okay, so that is basically that what we can find using this two equations, the classical physics equation and the electric field based wave equation, right? So those are that is the basic derivation of the wave equation, right? Apart from that, we have some more derivations that we need to do. So right, so we need to do some more derivations, and we need to prove that the wave equation can be represented in other ways, and also wave equation can be used to analyze the waves that are um, produced in our environment, and understand their like velocity, propagation constants, and also the frequency, um, I mean other parameters like its directions, its electric field and magnetic field component directions. Those things we can find using this wave equation, right? So this wave equation forms the basis to uh, find the parameters of the wave that is propagating. Okay, so we will learn those mathematical things, right? After that, we can, just finish the part about the wave equation, and then we can start talking about the uniform plane waves, right? Right. So that is basically the next task for as for the content, right? So apart from that, now if you have any questions, you can ask. Right, so we have shown the wave equation to be wave equation with respect to position and time uh, to be equal to the Laplacian of electric field equal to mu naught epsilon naught. So in here we are considering the free space. Therefore, we are going to add mu naught and epsilon naught, and then the electric field with respect to time. Right? And then we have also shown that the magnetic field is also showing the same behavior, same wave-like behavior in the free space and in other mediums. So this is the wave-like behavior that the electromagnetic wave shows, right? So the amplitude of the wave that is flowing depends on the medium through which it is propagating. That medium is defined using these parameters. So the value of mu naught epsilon naught will be changed to mu r into mu naught epsilon r into epsilon naught, depending on the medium that it is traveling in. Right? So we need to substitute the necessary parameters into these two mu naught and epsilon naught terms in order to consider the effect of the medium. Right? So then the solution, right? So the solution of the wave equation need to be found, right? So the solution for this equation need to be found, right? So solution of A needs to be found, for example, and the reason is we need to see like what is the behavior of the wave in terms of amplitude, frequency, phase, so on and so on. So in order for us to do that, we need to simplify these wave equations further, right? So keeping them in this manner will not be sufficient. We need to, process these equations further, and then we need to find the solution for the wave equations in a more simpler manner, such that we can evaluate its amplitude, frequency, phase, likewise some parameters which can be beneficial for us regarding the electromagnetic wave, right? The solution of the wave equation need to be found, right? Need to be found. In that case, in order to find that, we need to assume some assumptions, right? That will satisfy some conditions, right? So we need to assume some things. The reason being, otherwise, like finding the solution for the equation A and B is going to be like complex, and we need to at this moment try to find the behavior of the simplest electromagnetic wave, right? So in order for us to like analyze the most simplest electromagnetic wave, we are going to make the assumptions, right? So we are going to make two assumptions basically. So under those two assumptions, we are going to consider a very simple scenario where the electric field and the magnetic fields are only depending on the Z and time coordinates. So anyway, we are going to consider the most simplest type of wave to find its solution, right? So in order, before going to complex ones, we are first going to assume the behavior or consider the behavior of the most simplest type of electromagnetic wave, right? So the most simplest type of electromagnetic wave is known as uniform plane waves. We will get back to that later. So for the moment, we are going to make these two assumptions, right? We need to make some assumptions. We need to make assumptions, right? In order to find the answer, right? So we need to find the solution for the equation A. So we need to make some assumptions and consider the most simplest, right? And consider, we need to make some assumptions and consider the most simplest type of wave, right? Most simplest type of wave, right? So what is the simplest type of wave, right? So the simplest type of wave is the uniform plane wave, right? So we need to consider the most simplest type of wave, which is uniform plane wave, right? So most simplest type of wave is uniform plane wave. So in uniform plane wave, we have components, right? We have components of electric and magnetic fields on the XY plane, but not along the Z axis, right? The electric and magnetic fields depend only on the coordinates of Z, right? So the electric and magnetic field depend only on the coordinates of Z, right? And that is saying that the wave that we are considering is only going to have the electric field and magnetic fields in another like XY plane, where the electric field components are not along the Z axis. The components of magnetic field also do not fall along the Z axis. The electric field and the magnetic field only remains in the XY plane, right? So this is remaining in the XY plane. Okay, so no components of electric and magnetic fields are falling on this Z direction, right? So electric field and magnetic field components are only on the plane that is defined as XY plane, right? So E and H are only on the XY plane, right? So components of E and H are not along the propagation direction or the Z direction. Apart from that, we make an assumption that this wave is propagating in a homogeneous lossless medium with parameters epsilon and mu naught, and the conductivity equal to 0, right? So the fields, the electromagnetic waves or electromagnetic fields exist in homogeneous lossless with parameters lossless medium with epsilon and mu naught parameters, right? new parameters. Okay, so we assume that the electromagnetic waves is propagating in a certain, in this electromagnetic wave, which also means that electromagnetic field is existing, and that field is existing in a homogeneous lossless medium with epsilon and mu naught parameters. Okay, so the medium is defined using epsilon and mu parameters. So, okay, so the electromagnetic field is in this kind of a medium. Apart from that, we also have to find now the solution of the wave equation. Okay, so in order to find the solution of the wave equation, we need to expand the equation number A, and we need to consider these assumptions when simplifying the Maxwell's wave equation further. Right, so now we are going to like simplify the equations given by the number A, which is the equation of the electric field, which will propagate as a wave. Okay, so the electric field is propagating as a wave, and it is shown using these equations. It's proven using these equations, and also these equations show us that there's no explicit dependence on free charges, free electric charges. And so without free electric charges, electromagnetic waves can propagate in the free space. That is the basic idea that Maxwell's law gave us in comparison to Faraday's law and basically Ampere's law and Gauss's law. So, I mean, because of that, it was very very popular at that time, these Maxwell's laws, which were like creating a very, sudden discovery in the world. And this discovery led to people like thinking about the radio waves and how they are getting propagated through the space. And there was a scientist called at Heinrich Hertz who was able to experimentally show that the Maxwell's laws were correct. Right, so that is a little bit regarding the history. So this theory that was brought by the Maxwell's, saying that an electromagnetic wave can propagate in free space without the existence of electric charges or freely moving currents, right? So without the existence of varying current, the electromagnetic wave can propagate independently without the source that it created it. Right, I hope it is clear to you, right? That the solution, right, the solution of equation A, right? The solution of equation A, we can try to find by expanding the sorry, we will say this is the equation number M or something, right? M, right? The solution of M is can be, actually the solution of M is what we are trying to find. So the equation A, that expanding equation A, right? We can write dabba over dabba x squared into plus dabba squared over dabba y squared plus dabba squared over dabba z squared, right? And then we can write it as this, right? Like in here, I'm taking only the component of electric field along the x direction, right? Component of electric field along the x direction, right? So I'm going to consider this component only, and I'm going to consider that the solution of that component using these equations. So first, I'm going to substitute the Ex component on both sides. Okay, so I'm going to substitute this ES component on both sides, right? I can write then that since EX component is not varying with respect to X or Y, this is not varying with respect to X or Y, right? This is not varying with respect to X or Y. So therefore, the derivation the derivation here that we can take of the electric field with respect to X and Y can be cancelled. And the only part that will remain is the W squared over W Z squared EX ZT. Right? This one we can write as the mu naught epsilon naught, right? Mu naught epsilon naught W squared EX ZT over W T squared. So this is something that we can write as a simplified version of this first expression, right? So we can take this as the second simplified version. After that, we can also write the solution of this kind of a equation as the solution of this kind of a equation will be of the form EX, right? Now we are proposing the solution of EX in terms of Z and T, right? So here it's Z. In terms of Z and T will be equal to the equation where we have EX plus, right, cos omega T minus ZK plus EX minus cos omega T, sorry, EX minus cos omega T plus ZK. This is the general solution for an equation like this. The general solution for the equation of this form will be in this manner, right? So I will write it in a separate place, right? So there are two components to that solution, right? One component denotes the forward wave component, other component shows the backward wave component, right? And so we can write this in terms of Z and T, right? Z and T, right? This one I can write in terms of Z and T, and which I can write as EX plus cos omega T minus ZK, right? Plus EX minus cos omega T, but I will write it in a separate, in the same line. So I will write like this: EX minus cos omega T plus ZK, right? So this represents the forward wave component, right? Forward wave, and this represents the backward wave, right? So right. So this equation is a general equation which shows that there could be two forms for the electric field. One is the forward wave, other form is the backward wave. Sometimes there could be combination of this forward wave and the backward wave. So anyway, for all scenarios, this is the general solution for the electric field based on the wave equation for the electric field, right? So this is the solution for the wave equation on this is a solution for the wave equation on electric field. This is the solution for the wave equation that we derived for the electric field, right? So this solution represents that the electric field components are forming these two components, right? Can be consisting of the forward wave and the backward wave, and also the combination of both two components, right? Anyway, this is the basic solution, right? So out of this solution, in this in this section, we are only going to consider the forward wave component. Okay, we are only going to consider this forward going wave component in this section, right? Forward wave component in this section, right? in this section, we are only going to consider the forward wave component. Right? So once we are considering the forward wave component, we need to we can easily manipulate that component using our mathematical tools, right? I'm going to erase this. Right? I can denote this forward wave component, right? The forward wave component in different ways, right? The first way is that I can denote it using phasor domain. Okay, so I can denote this component in its phasor domain, right? Omega t minus zk, I can denote using the phasor domain, right? Using the expression, right? Real component, right? So real component of Ex uh, Ex Ej omega t, right? Ej omega t minus jkz, right? So this is the phasor domain representation of the forward going wave. So this is the forward going wave, right? This is the phasor domain representation of that forward going wave. So this is the phasor domain representation. Phasor domain representation of that forward wave, right? So why do I say that this is a forward phasor domain representation, right? How can I expand this? Right? Once I expand it, I can see I have Ex cos, right? I have Ex cos omega t minus kz, right? As the real part of the complex number that I can write for this expression. Okay, so since this is going in the forward direction, I put the plus sign, right? In here, I put the minus sign because this wave part is going in the backward direction, right? So I just add this plus sign to show that it is the forward going wave component, right? So anyway, we use this phasor domain representation to denote one component of the electric field, which is the component forward wave component. So anyway, now we are able to represent the forward wave using phasor domain, right? And then we are able to get some important results by taking the derivation of the forward wave with respect to the time, and then we can make some we can make some like good conclusions regarding the expressions, right? So I will show you now. I can take derivative of, I can take the derivative with respect to time on both sides, right? I take derivatives with respect to time on both sides, right? Once I take the derivative on both sides with respect to time, then I can write that cos omega t minus k z, I will write, okay? Zk, let's say zk. K z, zk, both are same, so I will write as k z, okay? K z, right, is equal to the real part of the, now the derivation with respect to time means you are left with the entire same thing, but the only thing adding is the component that we are adding in front of the j. So in here I'm left with this component, and however, like since I do not have any variation along the z direction, I'm only left with once I take the derivation with respect to time, then only this expression has the relationship with the time. This component is going to be constant once I take the partial derivative with respect to time, right? So this is going to be a constant in this time. So because of that, the derivative will be equal to j omega into real part of the Ex, e to the power j omega t minus jkz. Once I do that, I can write again that, right? I can write again that these two expressions are same, right? And that, right, I can write like j omega into, right? I can write the real part of this expression is this expression, right? So both these terms are equal, right? So I can write this as Ex plus cos omega t minus kz, right? In here also I have the same thing, w over w t Ex plus cos omega t minus kz, right? So since these two terms are equal, right? So since these two terms are equal, these two terms are equal, since these two terms are equal, I can get the conclusion that w over t is equal to j omega, right? So I can get this conclusion that w over t equals to j omega. Similarly, if I take the derivation with respect to z, right? If I take the derivation with respect to z, I can get the relationship, right? That if I similarly, if I take the derivation with respect to z, then the output will be w over w z is equal to jk, right? This is the derivation that we get with respect to z. Z is the displacement over the z axis, or the distance traveled in the z axis, right? So this is the second conclusion that we will get. So the first conclusion is w over w t equals j omega. Second conclusion is that the w over w t equals j k. So with these two conclusions, we are able to make the computations really easy, and we are able to simplify the wave equation into another form, right? So I will delete these parts, right? And I will write, right? So I'm going to derive the Helmholtz equation, the Helmholtz equations using the wave equations. Using the wave equations, right? I'm going to derive the Helmholtz equation using the wave equation, right? So the wave equation, is equal to this expression, right? So this expression, right? So if we consider that the wave is propagating in the free space, we can put mu naught epsilon naught, and we are also we are assuming that we are considering only the x component of the electric field, right? So x component of the electric field we are considering. Okay, so this is the relationship that is shown by the x component or the electric field in general, and it is the wave equation for the electric field, right? So if we want to solve this further, we can substitute, right, that w over w t squared is equal to j omega, right? By that knowledge, we can simplify this, right? We can simplify this as mu naught epsilon naught. Now instead of w over w t squared, we can substitute j omega squared, and we can be left with exzt. So in here, now we are having exzt on both sides. So because of that, we will take the Laplacian of the Laplacian operation plus, right? Since in here we have the minus sign, right? J squared means minus, right? Because of that, we are able to take plus sign onto this left side, and we are left with omega omega squared mu naught epsilon naught, right? into Ex Z T, right? So this is what we are left with in the in one side of the equation, right? So this is what we are left with once we have simplified the wave equation further. So this equation we call as Helmholtz equations, right? Right? Helmholtz equation. So this equation can also be derived for similar equation can also be derived for the magnetic field, right? So the only difference is in here the magnetic field component will be substituted, right? So this is the Helmholtz equation for the magnetic fields, right? So these are both Helmholtz equations. In here, this is for the magnetic field. This is for the electric field, right? Apart from that, you can see that in a Helmholtz equation, we cannot see any specific dependency on the time, right? I know that the equation components, right? These components are having dependency with the time, but specific dependency on the time, explicit dependency on time is not seen, right? So the in the wave equation that we derived earlier, we had the derivation of electric field with respect to time over 2 times. However, in Helmholtz equation, we do not observe explicit dependency. We do not have explicit dependency of the electric field with respect to the time, right? So the E field or Ex do not have do not have do not explicitly depend on the time, do not explicitly uh, behave a long time. Or right, I will remove this. It depend on time as in equation number A, right? As in equation number 1, let's say, as in 1, right? So in equation number 1, we had a section where we have the explicit dependence of the electric field on the second derivative with respect to time. However, in this Helmholtz equation, we do not have that explicit dependency of the electric and the magnetic fields with respect to the time, right? They do have dependency with respect to Z and the time. However, like in the equation, we do not have this kind of variation or derivation with respect to time in this Helmholtz equation, right? So all these parameters, they do not contain any kind of, they do not seem to contain any time. These do not seem to they do not seem to contain any impact from the time. So that is what is meant as not being explicitly depending on time, right? So Ex component, of course, it has a time component in here, but what we mean as explicitly not depending on time means the equation, the equation basically is not built on those time dependency operations. So these terms, they are not dependent on time, right? The electromagnetic field component, of course, is an input to this function. This is like an input, some kind of input to this function, right? If we have like any kind of input there, the output will be based on output can be found by substituting this equation, right? But however, like basic operations that I included in this equation do not depend directly with the time, right? It is shown that it does not, this equation shows that there's no explicit dependency on the time by using these two expressions, right? So in these expressions, there's no time parameter involved, no time parameter involved in these operations, right? So therefore, there's no explicit time dependency on this operation, as in this wave equation, which we learned earlier, which has explicit time dependence on the wave. On the electric, component, right? Electric field or magnetic field components, right? So the wave equation and its parameters, its functions have direct relationship with the time once we consider the wave equation. But the operations that happen in the Helmholtz equation do not have explicit time dependency, right? So the Helmholtz equation do not have explicit time dependency when it comes to the operations it has, right? Operations it has. I hope it is clear to you. If you have any concerns, please let me know. Okay, please let me know, and I will try to answer your questions. Right. So basically, the Helmholtz equations we have covered, and I think we can learn about the uniform plane waves next. Right. So I hope that you have gained some knowledge in this class. So I will end for today using in this point, right? So with regard to the mid exam, right? A lot of students called me and asked me about the mid exam. So like about the mid exam for the lateral entry students, I will be holding the mid exam in an online manner, right? So the lateral entry students will have the mid exam in online form, right? In the online form. Okay, so you will have in online form, you will have to uh, if you are going to participate in this, you have to like participate via the Zoom meeting. You have to have your video on, and then most importantly, you need to download the safe exam browser, that software, safe exam browser software you need to download before attempting the exam, right? Before attempting the exam, right? Before attempting the exam, at least 1 week before, right? Many days before, right? You need to download this and get ready, right? Get ready with this software, right? Then I will share with you during the before the exam starts. I will share with you a certain configuration file that you can run using this software. Right? I will share with you a configuration file that you can run using this software. Right, so this configuration file you can run in this software, right? And then what happens is that you will not be able to access any other websites while you are writing you can't access any other websites while you are doing the exam, right? So you can only access the LMS, right? Apart from that, note that this exam is done in online form, and this is a closed book exam, right? So you need to prepare accordingly, right? And the date, right? The date has not been finalized yet, right? The date for the mid exam has not been finalized yet, right? So after I have finished the uniform plane wave, I will most probably give the exam in the next week, right? So before keeping the exam, mid exam, the mid exam most probably will be held to you on the next week, Wednesday, right? Next week, Wednesday, that means 19th of July, right? So 19th of July, I will hold the mid exam for the lateral entry students, right? For the lateral entry students, I will hold the midday exam on 19th of July, right? And then by that time, you need to have the safe browser activated. So on Saturday, in this coming Saturday, I will have another lecture on uniform plane waves, right? Uniform plane waves, right? By the end of that, you will do the midday exam, right? So this Saturday from 7 to 9 p.m. I will have uniform plane waves, the lecture on that, right? So you will have this lecture, and then afterwards you have to prepare for the midday exam, right? We will have the midday exam on 19th July, right? If you have any questions, you can ask, right? That's all regarding the midday exam. So do not keep asking about this, right? I have mentioned these details during the lecture, right? So I will also send a message to all of you, all of the lateral entry students, to be prepared for the online exam and install the necessary softwares. Okay, so with that, I end today's lecture.